good.
Nico got it. Then the Nico got it. Oh, yeah. Perfect.
Good thing there. Oh.
Yeah, there's a weird thing here.
Yeah, this is the.
It's on yours?
It's, I guess we have to live with that, right?
Yeah, that's perfect.
Yeah. Should I start?
Good? Yeah, please.
Okay. Okay. Honest.
Did you guys already start playing?
Okay.
All right, well, thank you everyone for coming. Ernst Niebur will be leading this discussion. We're talking about a neural model that him and Stefan Mohammed developed 12 years ago, 13 years ago. So I think it'll be useful for the NTE folks. So thank you very much for the time, and we're looking forward to hearing about it.
Yeah. Okay. Thank you. Yeah. So this is somewhat. Can I turn this, or does it matter? Oh, maybe it doesn't matter. Yeah. So this is somewhat impromptu. So Mark asked me yesterday to talk about it. Of course, I'm happy to do that. Can you hear me? We have in the back.
Yeah.
Okay, great.
Thanks.
Yeah, so this is mainly the work of Stefan McClellan, who was a postdoc in my lab at the time, as Mark was saying, that 2009 the paper came out, but it's been quite interesting. So Stefan is now at the Allen Institute for Brain Research, and at the very end of this, I'm going to list one of the applications, which is actually in biology. So they use this model classify and characterize biological units, which is what he now does. So the title. So let me start with an overview slide from Eugene Zikevich from a paper, quite well-cited paper from 2004. And what he did is he listed a few of the commonly used single neuron models, computational models. And so what's the two axes here are? One is on the abscissa on the x-axis is the cost of implementation, how expensive it is, and the other is on the ordinate, on the y-axis, it's the level of biological plausibility. On the next slide, I'll show you what both of them how both of them are defined. Actually, the x-axis you can do right away. It's a number of flops, floating point operations, to solve the model for one time step. That's the cost. That's how he defines it. And then for the level of biological plausibility. So what he did, as you can read it, it's a number of features. So the number of features that a model can explain, and it goes from 3 at the top, so that is very poor, to 20 something at the bottom, which is very good. So this is we are not going to go into any details, but this is an overview of all the features that the models, so you can see them at the top, biophysically meaningful, that's the first one, and then it's sonic spiking, phasic spiking, sonic bursting, and all that. So he lists all these features that the model may or may not include, and then he goes for every model. He puts a plus if it can do it, the minus if it doesn't, and so that's what you see on the vertical axis. So the dots, I think it's mainly a guide for the eyes. There's no functional fitting or something like that, but it's the model seems to roughly follow this line, and you can see. So let's start with the very simplest one, integrated in fire. That's leaking in fire. So that's very cheap, only 5 flops. But it's also very poor, so that's not so good. And then at the other extreme, so what he considered at the time, I guess, the epitome of sophistication in modeling is Hodgkin-Huxley, and so that wins in the number of features. So it's good, 22 features, but he calls it prohibitive. and I have my quibbles with that, but that's that's the best one that he aspires any model can do. And then there are things in between. So you have, if you add one more parameter that will leak into the fire with adaptation, so that gets a bit better, and so on. And you have some that, for example, Maurice Ricard, which is kind of a weird one, which is really designed for some muscle, one specific muscle. It's a barnacle of all things, and that he is, for him, that's the only one that is biologically plausible. As I mean, like Hodgkin-Huxley, all the others are not. So there's some outliers here. There's one more outlier. This is his own model, and so he says it's very cheap but still very good. And we're going to talk about that in a few minutes. Seconds. Yeah.
Just a short question. Why is it so important to have one neuron be such super good? I mean, why not just take different neurons for different functions or functionalities? I mean, what's the problem with that assumption?
Well, I mean, there's different models have it's a compromise. Different models have different.
Exactly, but if I know what I want, I mean, I would be more the type of efficiency than of good, and just combine the neural models which are most efficient, but give me what I want.
Combine them. What do you mean by that?
Yeah, like, I mean, I could take an integrated fire model, maybe, and maybe integrated fire and bird, something like that, and then I have these two functions, so to say, biological functions implemented for a fairly cheap cost.
So you could go to his table and say, well, I want this and this and this color, and pick one of them. You can do that. But I mean, the purpose of this was kind of to give an overview of something. I mean, in general, what can we see about the properties of different neurons? And if you, of course, if you already know what you do, then yeah, you're probably better off with that. But many people want some compromise between the best and the cheapest.
Yeah, I was thinking, but because then I might start tweaking the parameters again to make them work like I wish. So it might add, given complexity, to have a more complex neural model.
Yeah,
Can do more, but might be difficult, more difficult to tune.
Well, maybe you need one more complex. Like there are people now saying that originating fire increase that better properties. Would you really like an originating fire in your network?
Or even the example we've been talking about this week of you have a system that you're going to let it train itself. And so you want it to be able to produce any phenomenology, because we see that in biology. We don't really know why it's behaving the way it is, but we want to see if our system can learn or reproduce that. And we don't, going in, we don't know what's the best model that will, what's the best parameters for the model that will do.
That makes better sense, yeah.
maybe I should also, since we're talking about some details, I should also say that I do not consider Hodgkin-Huxley the epitome of the best model in the world. It's not that. I mean, it's a very famous model, rightly so. But I mean, it's a model with one specific sodium channel, one specific potassium channel. And there is, I don't know, 30 sodium channels, 80 or so different potassium channels. There's all these other channels, chloride, calcium. So none of that is in Hodgkin-Huxley. So this is a somewhat simplified view, but I mean, it's maybe useful to have that, at least have the concept of this. So yeah, the other criticism I had was this here. So his model, which is proud, is actually better than Hodgkin-Huxley, because there's some things, if you look, so this is the model, the one in the red frame. So you see that in some cases he puts a plus for his model. It's some of these things that he can explain, but Hodgkin-Huxley doesn't. Well, Hodgkin-Huxley is not designed to be for this suitable for this matrix. And on the other hand, he's very honest and say it's not biologically plausible. It's not at all. I think the next slide, I'm sure that it's not plausible. And he says it. So let's look. So this is I put this here because many people use it in Mark. And so this is his model. So it's two states. It's a V, which is something. Well, the V sounds like voltage. That's implied by that. And then there's a second variable u, and this is why, as you can see, it's two ODEs, and the first one, the v equation, is a quadratic term, so it's non-linear. And so these two equations govern the behavior of the system, of the states, while it is below threshold. Threshold is 30 millivolts, as it says in equation 3. And when the threshold is exceeded by the voltage, then the voltage is reset, and u is set to some other value, u plus d, which is both of them are parameters of the system. It's a hybrid model, like several of the others, and also the models that I want to talk in detail about. It's also a hybrid model, so it has this well, it's an integrate part, integrate file. So you have the integrate part that is described by ODEs, and various numbers of ODEs, in this case 2. In some cases it's for others it's less or more. But then when you get to a threshold, you have have a discrete mode, and you just say there's a spike because you don't care about what the spike shape is. And okay, so this is a model, and the good thing is it can explain quite a bit what's going on. Oh, this is a stupid bar that says your screen sharing. Yeah, that's looks like it's going to be always in my, in my title. The good thing is this model, I mean, it was designed to be more complex, to explain more than the integrand phi, and it does. So he has like, whatever, he has 20 different phenomena. And so for example, it's a top right here, he has tonic spiking, and he has a spike adaptation, he has bursting, and various other things that he can explain. This is far beyond, obviously, what you can explain, what you can get in a linear environment. And then I should say that this is what at the bottom of each of these panels, you see a trace here and here and all that. So this is the current injected to generate the spike behavior that you see there. But even with some of these are very simple, just a constant, for example, in this case. Here they get a bit more complicated, but even if you have more complicated current injections, you're not going to get anything like that from a liquid environment. So that's good. So that's doesn't explain really, but it describes many different behaviors of neurons. However, well, if you go back to this equation here, it's hard to make sense out of it. I mean, where does 140 come from? And the 0.04 b squared, I mean, why 0 b squared? And if you look closely, so this, for example, this equation here supposedly for the voltage doesn't have even a capacitive current. And there's a capacitive current would be linear with V, be like this term, but it's positive. It's obviously unstable. So yeah, I mean, and second. So it doesn't even have capacitive current, which is the most basic thing that you have an integrator. So it does all the things that you have on the next slide, but it's somewhere I think to call it very smart, very nonlinear curve to get the behavior that you want to get. Yeah.
I asked you Eugene once.
What?
I asked Eugene once, how did you get these numbers?
Oh, well, good. I want to know.
Yeah.
That's what
No, but it's clever word.
It's clever, but my main argument, and I'm going to make this argument several times, is it's very smart. He's a smart guy. I talked to him.
Yeah.
He's a smart guy. No doubt about it. But the problem is it's not. It's ad hoc and it's not scalable. So that's my main problem. There are two problems. One, it's not scalable, and the other is it does not provide any insight.
Yeah.
Why is there no?
Ernst,
Yeah.
Ernst, yeah, I agree. This is not transparent if you look at equations. But when Eugene explains it to me, it was so this does the square and this 140, I mean, those were arrived from a null Klein analysis of the actual Hodgkin-Huxley equations, right? And there's not a direct physical connection, but it's derived, I guess, from a physical model, right?
Well, that's probably, I guess that's why he got his inspiration for finding this, when it's not that he was trying 140 and 135.
No, that's what numbers that were arrived at from null Klein analysis, right?
Yeah, but still it has this problem that it's not, certainly not biophysical. I mean, having a integrator without a capacitor in there, I mean, that defies the laws of physics.
Well, no. So isn't, I mean, the left-hand side of this equation, that's C times dV/dt, right? And the right-hand side are all the currents.
Yes, that's right. But
There's a capacitive current, right? No?
No, the capacitive current should be proportional to V, but with a negative sign. It's
Oh yeah, and that's because of the, if you're doing it, yes, if you would plot that V square and the V, right, there'll be a region where you get this negative slope. Yeah.
Of course, yeah. But I mean, it's just, to me, it doesn't look that it does not provide any intuition to me. And of course, yes, I mean, if you go to the four-dimensional Hodgkin-Huxley space, then probably there are areas where they just compensate in the right way and give you the negative slope. But it's not, to me, it seems not transparent.
If you were to plot it, it's probably more obvious than looking at the equations, right? Yeah.
Maybe, yes. But again, the other thing is that if you want to add a feature, if you're not happy with these 20 ones, there's something else. What are you going to do? Maybe you can go into the Hodgkin-Huxley space if you believe Hodgkin-Huxley is what you really want to do, which I don't think it is. I think there are many other currents that are at least as interesting as the sodium. I don't know exactly where I should be facing here. And then this specific sodium, this specific potassium current, then where do you go from there? So, yeah, well, put in parentheses kind of a bonus. I mean, this is the way you solve this, and the only way you can solve it really practically is by doing iterative. I mean, you go from t to t plus delta t, which is delta t equal 0.1 millisecond, and that's what everything does. And if you're a bit more sophisticated, you can do a variable step size and stuff like that, but it's always clock-based and step by step by step. Okay, and so what I want to talk about is I think it's a smarter way to do it, at least for many neuron systems, not for all of them. But that's I don't want to say this is really a big, every single model on this on this do the same thing. So that's it's not a criticism specifically of the Zikowicz 2003 model. So I think this is everything I already said. Is everything on here I already said, except for the very last line. Yeah.
Not event based.
Say again?
You said not event based. Can you elaborate on the other slide?
Yes.
Or the one before.
Yeah. Well, I mean that's I'll explain it.
Okay.
Okay. So the very last line is kind of the philosophy of what that was Stefan's idea. So well, we want something that goes beyond a leaking fire, which is very too simple for us. So we need some complexity that we need to add in that. And the other models, well, I don't want to jump again back to this overview there, but the other models of this type that are based on leaking fire, like the productive leaking fire and this adaptation, all that, they all put the complexity. They put it into the differential equations. So what Stefan's idea was to shift instead, keep the equation simple, and shift the complexity into the time when you have a spike. And it's not. You will see how we do this. It's not terribly biophysically plausible, but we know that many things are going on. And this is like the voltages, or the voltages changed by orders of magnitude, and there's additional currents that are flowing in and out. You know what's going what's going on in Hauptstadt. So it's not terribly wrong to assume that there's to put some of this into that period. So that's kind of a philosophical way. If you want, you can feel free to. It's not important. You feel free to ignore it. Okay. So this is what we wanted to have as properties, so that at least we don't have something where if we have a variable v that implies voltage, that it should be something, if it's an integrator, that should be something like capacitor in there, because that's what how we implement integrators usually. So something like that. And as you would see, it's not really biophysical what we do, but at least it's roughly, there's no weird stuff in there. Forget about the number of variables. The other thing is what I already alluded to is if we want to expand a model, we don't want to start going into whatever some high dimensional space and look at some null clients and twiddle our parameters, but have a simple way to add additional features. And there's a simple way, in the systematic way, that we have an idea what is going on. And these different mechanisms should not interfere too much with each other. And well, of course, if we can get an analytical solution, that would be great. And this is the answer to your question. Because if we have an analytical solution for our differential equations, then we can do event-based computation. That means we always start with initial conditions, and then the iterative ways, well, as I said earlier, you go from t to t plus delta t plus 2 delta t and so on. But if we have an analytical solution, we go from t, and then we see when the next change arises. For example, when the next spike arrives, and we can compute that because we know we have an analytical solution. So in one step, we compute the solution. We know it. The one spike is here, and so we have the solution. We integrate it, and we know that we have reached the threshold again at this time. So in one step, in one computation, we go from here to there. Okay, and this computation, I give you the solution. It's a bit more complicated than just take the first derivative of that and add it to the initial condition. But well, you don't have to. If you have, let's say, you have a firing rate of I don't know, 10 hertz. That means you have 100 steps to do, right? Instead of one. If you do iterative, you have 100 steps. Actually, if we take our what I said earlier, if we have a step size delta t to 0.1 milliseconds, and 1,000 steps to do that. And we can do that if we have an analytical solution. We can do it in one step. Okay, so that's what I meant by event, right? So if you can do that, what we get, and of course, well, this being Telluride, that's perfect for a year, and if you don't taste. So this is the model. It's pretty straightforward. So looks like the name that is being used by many people now is GLIF, generalized leaky integer environment. So it's let's start in the middle here. There's a reason why they're in this organism, this order. The middle should look very familiar. It's just the leaky integrand phi. So we have v prime temporal derivative, 1 over capacitance, injected current. Let's jump here, minus g times Vt minus EL. The EL is leakage potential or rest potential. Okay. Oops. Here. So this is so far, except for this term here that I discuss in a second. So far, this is exactly integer environment. Okay. If this term here is 0, would be the pure integer environment. So what is this term? So this term here is the sum of the J over currents, and these currents are defined here. And as you can see, they are very there's as many as you want, 1 to n, and here we sum over all of them. And there's very simple dynamics. They're simply exponential decay with in the time constants of which are three parameters kj, j for this current number j, okay, and so this is this, and importantly, this is where a good part of the complexity is, because these will be updated every spike, and I talk about it on the next slide, because this is only the neurodynamics below threshold. But something happens to these current with the spike occurs, but their dynamics is as simple as it goes, simply exponential decay. Yeah.
Yeah, I'm imagining that the IJs map to internal currents like iron and potassium current, sodium current and potassium current. So having two of them probably will correspond to those two currents. What happens if you have n greater than 2? And I'm asking this because I've implemented this in the class I took, and I couldn't tell what the difference would be if I increased n.
Yes. Well, so so this is where I would be more careful. I wouldn't call those sodium or potassium substances because they're not. They are exponentially decaying currents. It's not they're only present at the time of the spike. I mean, for example, a sodium current in a Hodgkin model, the sodium or the Hodgkin has to be neuron. The sodium current is really only present for a very short period of time, and it will change the sign of it. This is not. I wouldn't interpret them in this way. They're not really biophysical, so they are not. So this is where we should take this as
what happens when you have a larger n?
Okay. Well, two things. Well, two things. One is we never use anything more than 2. Very often we use 0. I'll show you in a minute. And it's just well, if you need something that you cannot get just 2, you take 3 or 4, whatever. I mean, there's nothing magical about the number 2, except that this is what we happen to use as a maximum. But it's mathematical construct.
When you say they are spike related, it's like that in the event of the spike, they get set to some fixed value and just decay from there.
Not some fixed value, I'll show you on the next slide. Okay, well, yeah, but at the time, so this is below threshold, this is all there is. When we exceed threshold, then something happens to them that I will show. Something pretty simple actually that I will show on the next slide. Okay. So any other questions? Okay, so the third one is an adaptive threshold. That's the third equation. And here's my pointer. So it's again first order differential equation. So it's very simple. So if the voltage goes up, then relative to the leakage voltage, then leakage potential, then the threshold also goes up. It's kind of like an adaptation, very intuitive. So the higher the voltage goes, the higher the threshold goes. But the second term is also we are trying to approach asymptotically yeah, it's very sensitive. We are asymptotically this approaches some theta infinity, some asymptotic value. And all these are 3 parameters, one theta infinity and A and B, and the case. And I think this is it. These are the 3 parameters of the model. Okay. G and so G is just the leakage conductance.
But something you define this.
Oh yes, yeah. I guess it's also. Yeah, you're right. Mm-hmm. Okay. Yeah, one thing. There are other. Adaptive thresholds are not uncommon. There's quite a few. There's quite a few models with that. But I put a little note in here. So sometimes their update happens at a spike. In this case, it's part of the subthreshold dynamics. So they're always adaptive. Yes.
I was going to ask the same question, but I wasn't able to hear it. Basically, if we're kind of say implement on the hollow fiber neuron with an AER input, but I need to compute the adaptive threshold continuously, or can I compute it on like a per event basis?
No, I didn't see the connection to the AER, but this is the threshold that's given by this differential equation. Here.
Can I
And
use that data?
there's also a change of threshold at the time spike, which I got on the next slide, but that's nothing to do with AER. But when the spike occurs, we update some of these variables.
The section A, right? And so imagine by the system where I'm only doing computations like on the event. So I get like timestamps coming in,
Yes.
and I only want to compute anything on like the next timestamp that I get in. That might be minutes into the future, essentially, like for like a hardware computation.
I still don't understand.
You're saying, can you calculate it when you have events as opposed to doing the numerical iterative solution? That's what he's referring to. For the threshold.
Okay, no, for this, I will show you like 2 or 3 slides down. I will show you the analytical solution for this set of equations.
Great.
From one event to the next one. So we take the initial conditions of what we need. Well, it's a first order here, so you need initial conditions. Those are the conditions, the values for I, for the different I's, if you mentioned several, and V and theta. These are the initial conditions. And based on that, I show you the equations for to compute these three variables for any amount of time. And of course, in practice, you want to stop this. You want to compute only until you reach the next spike, right? Because and then you have to reduce your thickness of spike with this super threshold dynamics and use the new initial conditions. And hence we can compute it for any time in the past or in the future, but it's not useful.
I guess my concern would be if the threshold is like say decreasing over time,
Yes.
but it decreases below like my current state.
Yes.
Like I'm not going to get another event in the future to then check if my current state is above or below the threshold.
Okay, so if your threshold goes below your voltage by definition, then it's a spike. So you can reach the voltage can go to the threshold, or the threshold can go to the voltage. That's very common.
I guess I was saying, so then that can happen in between spikes, right?
No, because the threshold, the equations are the solution is for all 3 variables, I, V, and theta.
So I guess you're saying we will be able to pre-compute the time when the neuron is going to spike next, based on the decay of the threshold below the voltage.
That's
Okay.
exactly right. Yes.
Although we discussed this before, this is assuming you know what your input current is over that time.
Yes, it is. And I've always so far, because we're talking about spiking, but we haven't talked about synaptic input. We will talk about that. But I mean, that's another thing. And that is a much more important point actually, because there's many more. Typically, a neuron gets much more synaptic events input than it generates outputs in the form of spikes. So also when you get a synaptic input, this is also an event. This also changes.
Don't you get, when you have, let's say, a lot of neurons, at some point it gets very complicated to forward this information. Like, I assume you should like substitute all the equations from one neuron to the next, because if you want to analytically like go in the future, I mean, you must know all the neurons and their behavior, right? I don't know, my impression is the more neurons I have, the more complex it gets to solve this equation in the future. It's very accurate.
Okay, so well, this I want to talk about the later, what we might do now. So no, it doesn't become more complicated. Simply if you have n neurons, then you have n systems of equations, and each of them may have different parameters. But I mean, you have to solve this equation, this system of equations in times.
Right, but it could also be like interconnected.
Yes,
It could have multiple influence, and I guess at some point.
That's right. And so how do you build a network? So the network is here IE is the injected current, and so this is when you have connections between neurons, then you have synapses go from one to the other, and the synapse, you can use whatever synapse you want, but all of them will inject eventually some current into that, and this is the injected current. So this is where the connectivity between them is.
Yeah, but that means there's also neuron state of neuron before, right? Which means then I substitute. So I could put in that equation like whatever the sign is times the neurons, the I of the neuron before. And this is what I mean. If you go along the line of having big network, this equation grows and grows.
No, that's not the case. You're entirely right. It does get more complicated. It's not complicated, more costly. And what happens is it does not get more complicated at all. I'll show you the equation for the synapse layer. But what does happen is that at every time you get a synaptic event, a discrete synaptic event, you have that is an event, and you have to restart from there. And so that makes it so if you have an highly interconnected network with many cross connections and a high firing rate, then that is probably not what you want to do. So if you have this type of network is probably not good. On the other hand, if you go, for example, deep into the more central areas of the nervous system, the firing rates are very low, sometimes 1 hertz or 10 hertz or something like that, and then your event-based method applies here a lot. So that's what I said. I mean, so in this case, high frequencies and high connectivity, this is not going to be my first choice.
So to kind of build on that, so like, let's say you have 100 neurons. The idea is at this time, you do the analytical solution for all 100. You find out which one is spiking first.
Yeah.
You progress to that point, and then you incorporate that information and do it again.
You could do that, but that would not be very efficient. And you actually have a simulator that I give you earlier. For this, the neuron that receives the input has to do that, or when it spikes, it has to do that, but you don't have to do that for the others, because there may be others that are not connected that are unaffected. So you just have to keep track of what neuron you can kind of
what its neighbors
leapfrog. And this one you can only go from here to here, and then you have to do them. Another one you might go all the way there. Okay. Any other questions? Okay. So, okay, so this is threshold dynamics. And now, what happens at a spike? Starting again with the voltage, maybe. So the voltage that's reset is set to a resting voltage, and that can be equal to the leakage voltage, or it can be something else. Okay, so that is very simple. Reset the voltage. This is one thing, or it can be below the resting voltage. Sometimes you can do it with mimic the overshoot in Hodgson-Huxley, but it's a free parameter what you want. The threshold, the threshold you set to also to some fixed value, except if it is already above it. Okay? So you set the threshold to the maximum of itself and the reset value, which is free parameter, and what happens to our currents? Well, they are set to R times itself plus A. So basically, what you can add a constant, and you can multiply it with a number. Okay. So that's the most general case. But for example, if you have R equal 1, then you you just add something to it. So you have an additive update. Or if R equals 0, then it's like a reset. Then you set the value of ij to aj, and you get rid of the old value. So it's very flexible. Okay, but it's still very simple again. There's no magic in anything of that. All of this are extremely simple operations and cheap in computation of cheap anyway. Okay, but there's no special source or something like that. And all these are free parameters. I guess the G2, as Mark said, I guess it's a free parameter too.
I think C as well. And C as well, the capacitance.
Yeah, I guess. And the only constraint is that theta R needs to be greater than VR. That's what turns out in the math. Okay, So that's it. That's it. So we have here now.
So I have a question, Ernst. So can you go back to the previous slide? So here's really where's the crux of the algorithm, right? What will give all these dynamic properties? Is there a refracted period, or is that inherent in the model?
I see. Would you get a refractory period in that? I mean, you reset the voltage to VR.
Yes, but does it stay there for a while, or does it get? Yeah.
No, I mean, once it's at VR, by this condition here, it's below theta, because VR is smaller than theta r, and theta could be higher, but then it would be even higher. So it's definitely below the value at this time. So it goes down to a lower value, and then if there's inflected current, it starts to increase. So I guess there's no absolute refractory period.
Exactly. Yes. Okay.
But there's a relative refractory period. We have no other constraint. But this is all you get. There's no additional constraint.
Although you could probably engineer it such that effectively there's an absolute refractory period, but set in the parameters in such a way, right?
I guess you could impose an additional condition, but that seems, I don't know if, I would think that if you put VR low enough, then for all practical purposes, you would have something like a very refractory period.
It's a little wonky, but maybe you could create a negative induced current from the spike that'll like artificially keep it low.
That's yeah, and that's another, yeah. Sometimes, oh yeah, I mean, VR negative.
Yeah.
But I mean, what do you think absolute refractory period is important?
It's something you find in biology. There are neurons which
Yeah.
do not fire again for a given time.
Yeah, I know. But if you
It's at the limit on the maximum spike rate, right? Yeah.
it limits the spike rate, yeah, that's true. But
you don't have an explicit refractory period in Oscar Huxley, for instance,
No.
or anything, right?
no.
Those just fall out from the channel dynamics. It comes about.
Okay. Okay, so yeah, the first thing, let's jump to that, rich behavior. So following the example of Euclid, we have also, I think, 20, 4 times 5. So we also, it's not the same, but I mean, we think actually these are more relevant. It's something like a resonator, just like that, which was weird. But also all these are behaviors that are observed in various neurons. This is just steady state firing. So, oh yeah, I should mention that we don't plot the spikes as vertical lines or something like that. So, but the way this works is you have a time on the horizontal axis and V, let's call it the voltage, on the vertical axis, and then you have always at the bottom you have the injected current. So in this case, you have injected current with this constant, and then you see while you integrate. And then you reach a threshold, which is the dotted line, and the spike is simply denoted by a big black dot. So in this case, we inject for this set of parameters that we choose here for this neuron, we have, if we inject a constant current, we get a sequence of spikes which has a constant frequency. So that's maybe the simplest case. Okay. In this case, we have from the outside, we get very similar behavior because we inject a constant current, but but the spike frequency is lower, but it's the detailed dynamics is a bit different because it stays so long there. It's called a class 1 neuron. I don't want to go to details. There's also somewhere there's a class 2 neuron, but the difference between these two is simply different parameters. And there are some, more interesting ones. Let's see, for example, here this one is, I like that because I used to work with nematodes, and this is something that you find there quite regularly. You get a rebound spike. So people used to call it anode break. So what you do here is you inject nothing. So here the voltage is 0, and then you inject a negative current for quite a long time here. Okay, and well, not surprisingly, the voltage goes down. That's what you get exponentially, and then at some point it settles close to the reversal potential, or reversal potential for this voltage for this current divider that you get from this injected current, and then you turn it off. You turn off the current, and what you get is the voltage goes up very rapidly, and because we get this only from the threshold, from the adaptive threshold, it catches up fast with the threshold, and you get a spike here. So it seems a bit paradoxical. You inject a negative current, and that generates a spike, right? But that is something that happens in quite a few neurons. So this isn't something we get very cheaply in. And whatever, we don't want to go through all these bursting and periodic bursting, all this kind of stuff in there. So so that's good. And all, yeah, okay, maybe let's get to the next one. So this is actually a table. This is from the paper, a table of the parameter that we actually use. So as you can see, all these. So this is for A to T are the different the 20 different behaviors. And what these are the names, and as you can see, we have different currents. For example, the first one we have inject 1.5 in this unit, the second one a much smaller one, and so on. But the only parameters that we changed, the change between them are A, that was the first one in the adaptive threshold, and the two A terms, the additive terms in the spike dynamics. We don't. All the other parameters, they have values, of course. They're here, but they're identical for all the others. So it's not that we have like 2,000 parameters that we need to fit 20 different behaviors. They're all constant. We don't make use of, for example, the R times I in the reset in the reset of the currents. We only use the two adaptive parts, and in the two additive parts. And as you can see, in half of them or more, we don't even use the currents. All of these here, the last one actually too, they're all 0. So all these behaviors here we will end from the adaptive threshold. So you can see that if this is not by no means limit, even though we only have two currents at the time of the spike, we only use half of the degrees of freedom that we use, and even those we don't use in our cases. So if you can get much more complicated behavior from this system, much more realistic behavior. Okay.
Short question before you release the table. The complete right column is the input current.
Yes.
Yeah. So that means if I want to have a tonic bursting neuron, it depends on the input current, because this might be something I cannot control, right?
Well, I mean, the idea is that you can certainly inject a current.
Right, at some point, yeah, but then later in the network, I use that.
Oh, well,
power.
yes, well, of course. I mean, this is a single neuron model. When you talk about networks, you have to specify synapses, what the synapses do to the other neurons and all that. But this is a single neuron model.
Okay, I was assuming, we have just a fixed input current, and then we see what these kind of parameters will treat the neuron to do. But yeah.
I didn't understand that.
No, then we have one fixed input current always, like we fix the resistance or the capacitance, and then we treat these three parameters together, given behavior of the neuron. But this time we use the input current as a parameter to change the behavior of the neuron.
Well, imagine that the current can be normalized, and that's your new parameter.
The parameter, no, the current is not a parameter. The current, it's one parameter, it's IE of T, right?
Yeah, right.
That is not a parameter. That's
Not exactly, but that leads to different behaviors of neurons.
Yeah, but I mean, it's the same as in the Sikovich. I mean, you have, for example, whatever, in the one that we talked about here, you have first you inject 0 current, and then you inject a negative current, and then you go back to 0. And that is the way you do the experiment. If you have a neuron then exactly what you do. You inject nothing, then you inject a negative current, you do it for a long time, and then you set the current to 0, and then you get a spike.
So, thanks.
Any other questions? Okay, so, okay, right. So, right. So basically, yeah, we talk about the synapses in a moment, but I wanted to say that again, this is not a kind of a black box where we have a 140 and a 0.3 and do it 5 times something in there. Here we can control that. So that I think it's, at least to me, this is much more understandable than the complex dynamic, because here we have very simple dynamics for the adaptive threshold, and the other the injected currents we can control in a simple way. So to me, this is more intuitive. So the last thing is on this slide, a word of warning. Even though I talk about the voltage, we make no claim that any of the parameters, the voltage or threshold or anything like that, is really biophysically a voltage. The only output that we kind of stand behind is the sequence of spikes and spike pumps, in other words. So this is the output. Everything else, even though I think it makes more sense, but not in the sense that I would say this is biophysical. We only say, well, this is treat, if you want, treat it as a black box, and you put in some input current and you get out the spike. This is what the model does. We don't claim anything more. Okay. All right. Don't know what you have here. Oh yeah, right. Okay, sorry. And I'm not, I mean, it's not hard, but it's lengthy. So basically, what do we have? So this is these equations are linear. I mean, if you go, if we want to go, let's go back. This is all of them are linear. So I is on the right hand side. The equation for I is linear in I. Equation for B is linear in B and I. And theta is linear in theta and B. So this all this is a linear matrix. It's a matrix. It's a linear system in I, B, and theta. Okay. Furthermore, it's triangular. That is, by the way, why it's written this way. It's a triangular matrix, so it's easily diagonalizable over reals. And you can show there's one stationary solutions, and even for any number of spike news currents that you want. And well, you just go through this linear through this triangular matrix and do it step by step, and then you get the equations for I is simply exponential decay, and then you get for the voltage so you get this exponential decay too, but I mean you have to take into account the I's, so this is why I wrote it this way, and for theta it's the same thing, but now all three of them play a role in that. So this is the complete solution. The only assumption is that the eigenvalues are distinct, and the initial conditions are they appear here in various places. Okay, so that's it. And you see.
And also, this assumes there's no external current between two spikes, right?
Two spikes are, if there were. Yes, you're right. You have an external current, but you cannot have something like a synaptic input at the time.
Yes.
Between them, because that would be an event. Then you have to stop there, take these new initial conditions, and start from there again.
And actually integrate then whatever the exponential decay that you have of the synaptic conductance or so, right? Yeah.
That's right. That's right. Yes. Mm-hmm. Okay. So no iteration required. We can. And that's basically, yeah, okay.
Before we go, so how exactly, so okay, so you have this equation, what exactly do you solve? You solve from V equals theta? Like what is the, when you...
This is for the three variables. We have I of t, B of t, and theta of t.
I guess, but okay, so we're trying to calculate when there's an event. what is the,
Oh, I see. So you mean when we stop?
yeah,
So,
exactly.
the point when we want to stop is when v of t gets greater than theta of t.
Okay. Yeah.
Go back to the table. Or
It's a table.
I'm sorry, the one
This
with the parameters, yeah. What is over, that's I, okay, I see. See, I became confused when I saw that there was a closed point solution for I, because I was looking at I as an input. But in fact, the I sub whatever I read is the input.
I.e.
I is the
Yes.
input, okay.
That's it. Yeah.
Excitable input, okay.
It's in fact the current. And I mean, this is why obviously it's just shorthand for we have constant in this for these simulations, we have a constant with steps in between it. So the values are shown there.
You go to the analytical, so can you go to
Yeah.
the Multiplier? Because if we want to solve this now, so basically we are interested in t+1, like the next event time when this neuron, given there's no other events in the meantime, and they
Yes.
need to be computed. Yeah, when would be the next candidate time?
That's
For the
exactly
first, like,
yeah.
Is that easy to solve, or is it possible, like, because it could be that this equation is like complicated, you need to do some root finding algorithm to find
Yes.
like the first time when it was fine?
Actually, you're right, and I didn't want to put it here because there is actually a root finding algorithm. It turns out, what's his name, Brett, B-R-E-T-E, French guy. I mean, there is a you can find these the terms and terms as roots of a polynomial, but it's actually even simpler. It's even simpler than it's used. I mean, you mentioned the paper.
Okay.
Yeah, but you're right. You have to do that, but it's easy to do it, and it's pretty good. Yeah.
I think we had also talked about this before. How does it work if your input current, like if you define it over time, but it's not just one scalar, but it's dynamically changing, you can still put that into here?
Well, then I'm not sure if the root finding thing works there, but you can do it from this. Yes.
Okay.
I mean these are functions of time. So I will do. Okay. And I'm pretty close to the end. So okay, so getting back to this. So where does this model fit in this here? So it's what I think I said that, but what you need to say. So this is the implementation cost per time on the horizontal axis is the implementation cost per time step. But we don't have a time step. Okay, we don't. All of these models, the solutions are iterative. So that's how you can compare them on this basis, but we don't. So I think so. The best way to characterize our model here is like this. We don't know. It depends. It depends on the specific system. So we know that we are at least, or as realistic, at least as Zikovic. So this is on this scale. We are somewhere here. We certainly have our 20. We easily can fulfill our 20 different features, but how much time it costs now, we can't say per iteration because we don't have iterations. In the case where you have this unfortunate situation of having lots of inputs and lots of outputs, then we will be prohibitive, as it. In cases where we have, like in orbital robotics, something with low firing rates, then we will be super efficient. So we are somewhere there, and where it is, we have to look at low.
And actually, Ernst, this table doesn't make sense at all. Look at Fitzhugh Nagumo. That's supposed to be much more expensive than Zikovic. I mean, Fitzhugh Nagumo is just two equations. I mean, I don't quite understand why it'd be 72 flops. Yeah.
Yeah. Talk to Eugene. I don't know. It's not my table.
Also, the integrated bias also unfair because you could also solve this analytically in principle, right? You could also for the leak integrated bias, you could also go from step to step, right? So it's like I think it's maybe the table is not super fair.
Yeah, you're right. I mean, you could do this step by step. You could do, but I mean that would mean you would also have a horizontal line. And of course, I mean, I didn't say that when it's pretty obvious that from the equations, I mean, if you put the A in the adaptive threshold and the R and A in the spike induced current equal to 0, then our model is the leak right now. So you can do exactly what we're doing here. You can, of course, we can do it much easier in the straightforward. Okay, so this is networks. So this is we know by now, and now the injected current. We already talked about it. So you can take whatever model you want. Every synapse is going to inject the current. That's how it works. So you could do something like here, which would be like a artificial neural network component with the weights. Each time there is the spiking artificial neural network. So this is the spike train usual format, like here, a sequence of delta functions. Or you could, somewhat more realistically, you could have a conducting synapse. And in both cases, you can take whatever kernel you want for your synapse. But given the other equations, it's very convenient if you take an exponential decay because everything else is exponential. But you don't have to. You can do something else. And what? Yeah, right. So this is a blurb for. So we built a event-related neuronal simulation tool. It's written in Java. You can download it. Source code. And you don't, probably your machine already has a Java machine, so you can just run it, don't have to compile anything. And the performance, well, because it's event-based, it's limited by total connectivity and firing rates, as we discussed several times. But you can have 100,000 neurons very fast. And there's also support for multiple machines, but the weak point is it's not used. We used it quite a bit, and we have, for example, yeah, that's another thing I didn't mention, but we used it for one paper, turned out very well, very nicely. There's another advantage of this event-based solution that was crucial for this paper that we wrote. It was with chaos and in neural systems, self-organized criticality, not chaos, self-organized criticality. And we could not have done it with any of these other models because this is the exact solution up to machine precision. Everything else is approximated. Okay, so you have, and that means why is this important for this research that we did there? Because for these self-organized criticality work, it is important to know what neuron specifically pushes another one over the threshold. And if you have have a finite interval where typically multiple events arrive, then you don't know that, and then you lose causality. And this is causal up to the limits of machine precision. So that's a bonus that we have, and that we used our or similar to that. Otherwise, it's not very heavily used. That's to say the least. So the documentation is not exactly stellar. You had a question?
Yeah, I was just thinking about how to implement that model. Let's assume we have a sensor which is frequently pulling the sensor readings, and then we emulate a neural model to, I don't know, have a given behavior like we use for the tactile now.
Yes.
Would you suggest to use this neuron? Because from my understanding, I don't know, if you go then back to this kind of clock-driven updating, it might not be the most useful implementation, but maybe I missed something.
Okay, I think for me, there's two reasons. One is this question of efficiency. The other is a question of transparency, of understanding or having an intuitive feeling what is going on there. Yeah, you have to see. I mean, you may even do something like this. I mean, for example, as in the study that I just mentioned, I mean, it simply would not be possible. I don't know if it was efficient. It may be more efficient to do it in the specific neural networks that we had, but we would not have been able. We needed causality. We need to know which neuron push this together on all the threshold. So yeah, nothing we can do. We cannot simply use an iterative method for that one.
I guess kind of similar to that question, would you say that it doesn't make sense to use this model if you're going to end up doing it iteratively? Like it only makes sense if you use the analytical solution.
No. What do you mean? You can't do this. I guess you could do this iteratively. If you wanted to, you could do this.
Like just like the other models. I'm saying if you're using this in that iterative way, the way we use all the other models,
Yes.
it doesn't make sense to use this model. You should only use it in the case where you use the analytical solution from a computational perspective.
I think the point is when you face the sensors, you don't know how it will change in the future. You cannot at time t derive in the future when the spike will happen because you don't know what in between happens. So you have to do this kind of iterative thing because each iteration gives you a new input you have to read.
So if you have discrete events happening,
Exactly, yeah.
yes, then you're not going to win with this. Yes. You,
That
you
was
might,
okay. That was, yeah.
you might still win with this iteration and all that. And if in the probably rare event that causality is important, and most usually, I mean, typically it is not, then you would have to use it. But yeah.
So if you're running something in real time.
Yeah, I think it was just to that point. I mean, it isn't in the end, every time you get an input, you need to make an estimate for when now, what is based on this input now, what is the next time I expect the neuron to act? And I need to update this whenever I get a new input. So it's a matter of like how costly is it to compute this prediction.
That's right.
Yeah.
And then we're back to the many spikes not feasible.
That's right. Exactly.
Right.
Feasible, but costly. Yeah. Yeah, well,
As it was in hardware.
Oh, no, it is.
hardware. Oh yeah, next slide. Thank you. Yes, there's at least two hardware interventions that I know for. One is one is in Florida and Andre von Schleich. The other is by Hopkins groups, Ralph and Andreas. Ralph actually he has an array of more than 2,000 of those implemented. So you can buy it. I don't know if you can buy it. You can. We have that. The other thing I mentioned that at the very beginning, I think it's my last slide actually. No, I have a summary slide. It's also used in biology. So as I mentioned, Stefan is now at the Anna Institute, and they have these huge databases of well, they have a lot of anatomy circuitry, but they also have physiology. So they characterize spike behavior of 100 to 600 million different genetic line cells from mouse cortex, and yeah, found that with this excellent behavior. And now, because this is the tactile group here, so there is at least two studies where this model has been used for modeling primate centers in hand that we heard about this morning. One is from our own group, Dom et al., and the other is from Sleeman Bensman's group. And so yeah, I recommend that.
So one interesting thing, so the IFAD array, so that's like one of the hardware implementations, and so they don't implement the model directly. They basically do like a simplified version of the model. So they show like he showed 20 behaviors, and then they did the hardware simulation where they showed like 10 of them. It wasn't the full set because they don't implement every feature. But the interesting thing is that the way that they implement these neurons is by combining multiple regular integrating fire cells together.
Two, I think.
Yeah.
I think if you want to have just a regular leak in the nerve, you get twice as many bit 4,000 instead of 2,000.
So it's like kind of already leveraging the integrating fire hardware architecture that's already there.
Okay, yeah, well, my summary, I think. Do I want to point out something? Everything, yeah, well, you can add currents, but you don't really, we never needed it so far. I think I talked about everything. Yeah, so okay. Any other questions? comments.
Just a question. You stated there is this software that simulate your neuron. Consider that we wanted to implement it in Python and everything. Did some people, maybe Brian or I don't know, whichever other simulator implemented your neurons? Like, are you aware of?
Yeah, I mean, so there is actually this one, the SourceForge page is maintained by Tim. I might actually know him. He was an undergraduate at Caltech when we were both there, David Croft. So David Croft, he's a software engineer. He works, I think now he works for a different company. I think now he's at RateNet for a while. So he is, so he kind of maintains it, but I mean, he's just volunteering for doing the full interest. And he has, he's in his free time, in his spare time, he's working on implementation in Rust, which I didn't really know before. It's a new, apparently new and shiny, for me, new, probably you guys all know that language.
I think originated from Mozilla Corporation.
Oh, really?
Yeah, and I think they designed it because basically they wanted a language that compiles to something as fast as C or C++, but without the risk of all of this memory leakage and stuff like this.
Sounds good. So he's, but I don't think it's that. I'm not sure that anything already on SourceForge on that. Because
And is that Python wise, you know, like, for example, Python?
Python, no, that's a travel.
Yeah, but you know somebody.
I don't know. Okay.
Okay.
Thank you. I still have enough to say any more questions from Zoom now. I guess not. Okay.
Thank you.
Sure.
Thank you. Great talk, Ernst.
Thank you.
Oh, it's on the side. Whenever you write it. Always to stop recording. No, you. Oh, it's recording. Oh, yeah, recording.